Hello children, welcome back to the channel. Today we will be starting the topic of rigid body and its rotational motion. Now what is a rigid body? That is the first question that we need to answer. A rigid body by definition is a body whose particles maintain their relative positions while they are moving. What do we mean is that let's say we have a system of particles, say this 1, 2, 3, 4, 5, right? So this system of particles, these particles interact with each other with their internal forces. And if it is so that the entire system, when it's acted upon by some external force, say F, external X on it, and the body moves or the system of particle moves, the distances between the particles, that is between these two particles or these two particles or these two, so distances between all the particles, that their relative positions with respect to each other do not change during their motion. If they are fixed in position with respect to each other, then they are known as rigid bodies. Now the examples of rigid bodies are numerous. All the bodies around us, most of the bodies around us are rigid bodies. For example, this pen, it's a rigid body, because if I move the pen from one point to another, it maintains its entire shape and size, right? It doesn't change. What it means is that within the, if you look at the pen from inside, the position of its cap or the position of the tip, their relative positions are the same. They are not going to change if it's moving like this or it is rotating. Whatever we do with it, the position of the relative position of the different points or different particles within the body will remain the same. If it is so, then such a body is known as a rigid body. So a rigid body by definition is a body or a system of particles whose internal particles relative position remain fixed with respect to each other when it moves under some external force. Okay, so if the relative position of the particles do not change, then the system of particles, say, or the body, whatever its center of mass is, say this is the center of mass of the system of particles that we have, then this or the rigid body we have, we'll call it a rigid body from now on. So this center of mass will hold its position with respect to its constituent bodies, which means, let's say, the center of mass of this pen, if we consider it as a uniform rod, then it will lie at the center of the rod or center of the pen. So when it moves around, whatever direction, whatever way, whether it's an accelerated motion or it's a retarded motion, whether it's a rotational motion, whatever kind of motion it undertakes, the center of mass will remain at the center of the rigid body. It will not change its position with respect to its particles. So the center of mass of a rigid body remains fixed with respect to the body as a whole. For any kind of body, whether it's a discrete mass distribution or a continuous mass distribution like the pen or any other object you take, maybe the duster, the center of mass of the duster will remain where it is. It will not change its position relative to itself. Okay. Yes, of course, when the body moves, we know that the center of mass also will move, but it will move along with the body, and its position with respect to the body, different particles of the body will remain the same. Which means that if it is at the center of the duster, then it will remain at the center of the duster, whether it moves or whether it is stationary. Okay. Now, the translational motion of rigid bodies is the same as we have already discussed for system of particles, where of course in a system of particles, the particles' relative positions could change. For example, if you have a system of particles, say we have the room full of air, it becomes a system of particles, right? The air molecules become the particles, but air molecules are free to move about. So when the air molecules are moving about, then the center of mass might be changing, right? However, in case of rigid bodies, the molecules or the particles will remain fixed at their relative positions, and so they will not move. And so, when we talk about the translational motion of rigid body, it being a system of particles, whether with discrete mass, discrete distribution of masses, as we have just seen, or continuous distribution of mass like the pen or the duster, as we have said. When we talk about translational motion, it will remain the same as we have discussed in my previous videos on system of particles. Okay. What we are more concerned right now is how rigid bodies behave when they undertake rotational motion. Now, when we say a rigid body is under rotational motion, rotational motion of a rigid body. So, let us say we have a body of any shape. Let's say this is the shape of a body. Okay. So, different mass particles are distributed over it. And it's a rigid body, which means that the mass particles' relative positions will not change whichever way they move. Now, let's take an axis at this point. And let's say the axis is perpendicular to the plane of the board. So, the axis is into the board, right, like this. This will represent the axis. So, if we rotate the body in the plane of the board, what will happen? Say we rotate it in the counterclockwise, so what will happen is that the body probably will after some time be like in a new position. Let's say this is the new position of the body. So it has moved from its initial position to some new position. Okay, about this axis. So what will happen? All the constituent particles of the body will be moving in the plane of the board. So when all the constituent particles of a rigid body move in a plane or move in parallel planes, because it doesn't have to be a two-dimensional object. For example, if I take the duster and put an axis like this here, if I have an axis here, and it will move, rotate, right, about this particular axis, this particular point. When it moves, the entire body moves, right? When the entire body moves, what will happen is that it will move perpendicular to the plane of the duster. So the particles at this end here will move in a plane, vertical plane like here. Another particle at the other face of the duster will move in another plane, but they are all moving in parallel planes. When these particles moves in parallel planes, when all the particles of a body, rigid body moves in parallel plane in a circular path, this about a given axis which is perpendicular to the plane of the body, then we say that the rigid body is executing a rotational motion. So when all the particles of a rigid body are moving in parallel planes with respect to certain axis which is perpendicular to the planes of rotation, all the planes of rotation. So if I take this axis and the object is moving like this, so this is the plane of rotation and the axis is perpendicular to the plane of rotation. Under such condition, the rigid body is said to be executing rotational motion. Okay, now let us consider that there was a particle here initially. So after the body has rotated from here to the new position, the particle would have also moved from here to a new position here along some arc. This is a circular motion, right? So it will move along some arc. It will be executing a circular motion here. Okay, so the arc length it has produced is this much. Let's call this some value. Let's call this L. It has moved by a distance of L. If I consider another particle which is much nearer to the axis, here say, it will also have moved in a circular path with the same center, but the radius of the path will be smaller, right? So it reaches to this particular point. So this path length here, this path length executed by the second body is say L2. Clearly L2 is smaller than L1. There by visual you can say this smaller than L1 is greater and L2 is smaller because L1 is farther from the axis. So when we talk about rotational motion, if we say the linear displacements of the particles from one point to another, they will vary. However, if you notice, since they are on the same lines, the angle subtended by the initial and final positions here, this angle, say theta, will be the same for both the particles. In fact, for all the particles, when you move, when the rigid body rotates about a given axis, for a given time, for each of the particles of the rigid body, the linear displacements will be very different. However, the angular displacement for all the particles will be the same. So it becomes easier for us to understand the motion or rotational motion of a rigid body if we talk in terms of the angular displacements. So what we will do, we will first recapture what we already know about the angular motion of a particle and how to adapt it to rigid body, and then move on from there. Now we already know the certain things about rotational motion of a particle, right? Let us say we have found some examples, or we have already defined certain types such as angular velocity omega, angular displacement theta, angular acceleration alpha, and we have defined alpha as d omega by dt. Rate of change of angular velocity is known as angular acceleration. Again, omega is d theta by dt, rate of change of angular displacement, where theta is the angle subtended when a body or particle executes circular motion. Like say this is the center of the circle, so it moves from some position to a new position along this, then this angle is theta, right? We also know that angular motion or circular motion is an accelerated motion that we have already discussed in the motion in 2 dimension chapter. If you haven't seen my videos on that, you might please refer to my playlist. The link will be given in the description below. You can find all these basic concepts here. Okay, now coming back, if alpha is given by, that is angular acceleration is given by d omega by dt, then we also have that d omega can be given as alpha dt. So if we take certain conditions that when t was equal to 0, when we started the measurement, let's say omega, that is angular velocity, was omega naught, the initial angular velocity, and when we concluded the measurement, that is when time is equal to t, the angular velocity has become omega. Okay, we are considering the case of constant acceleration, angular acceleration, not variable angular acceleration. Then the net angular velocity, change of angular velocity, is equal to alpha into dt. So what is the net change? We can always integrate this. D omega must be equal to alpha is a constant angular acceleration dt, right? The limits will be when t equal to 0, omega was omega naught, and when time becomes t, omega becomes omega. So if we solve this, we get omega minus omega naught equal to alpha t, or we can say omega equal to omega naught plus alpha t. Quite similar to the equation of linear motion, where we had velocity v equal to v naught or u plus not alpha, this is at, right, and this is alpha t. So this is first equation that we have found, omega equal to omega naught plus alpha into t. Okay. Now, if we call in the help of the other equation, that is say omega equal to d theta by dt. omega equal to d theta by dt, we get d theta equal to omega dt. Okay, now let's say when t was equal to 0, let's say angular displacement theta was equal to 0. We started with the x-axis, say, and when t becomes t, the angular displacement becomes theta. Then we must have integration 0 to theta d theta must be equal to integration 0 to t omega dt. However, we already know that omega is equal to this, so we can say this is equal to integration 0 to t omega naught plus alpha t dt, which will give us the right hand side as omega naught t plus half alpha t square with the limit 0 to t, and the left hand side will be theta with 0 to theta. So theta angular displacement will be given by substituting the values. We get omega naught t plus half alpha t square. So that is to say theta equal to omega naught t plus half alpha t square. S is equal to ut plus half at square. Quite similar to that, right? Now, if we come back to the previous equation, the first equation, or the equation of acceleration, alpha equal to d omega by dt, right? We can always rewrite this as d omega by d theta by dt. We can always write it this way because d theta will cancel out. But d theta by dt by definition is omega, right? So we can rewrite this as alpha d theta equal to, this term will come first, say omega d omega. Okay, now if we consider when t was equal to 0, omega was equal to omega naught, and at that time theta was equal to 0. We have already considered this case, right? And when t equals to t, omega becomes equal to omega and theta becomes this. So from this equation what we can do, integration alpha is a constant, right? D theta, and theta we have to integrate from 0 to theta equal to omega d omega, right? And this has to be from omega naught omega, right? Omega naught to omega. So if we integrate this, what we get? Alpha will come outside, so integration d theta is theta with 0 to theta equal to omega square by 2 integration omega d omega. This will be from omega naught to omega. Cross multiplication and rearrangement will give us, let's say this will be omega square minus omega naught square equal to 2 alpha into theta. That is our third equation. Omega square minus omega naught square equal to 2 alpha into theta. V square minus A square equal to 2AS. Right, these are the basic equations of kinematics for rotational motion, rotational kinematics. Okay, when a body is moving in a circular path, when a rigid body is moving in a circular path, this equation will come in handy. A simple problem here. Let us say a rigid body starts from rest and it covers, makes and rotations in t second. Then what is alpha? Omega naught is equal to 0. The rigid body starts from rest. So a body was at rest and then a force or something was given so that it started accelerating with constant acceleration, angular acceleration of alpha. It is found that in time t it has made n complete rotations. What will be the angular velocity or angular acceleration? Now, to do this, first thing we need to know which equation of motion we will require, rotation we will require. So, what we can see here is that we have the total angular displacement. So, this angular displacement, the equation is given by the second equation, right? Here omega naught is 0, t is given, alpha and theta. Now, if we can find theta here, we will be able to find the value of alpha. So, what is theta? The angle subtended at the center in time t. Now, if something is moving in a circular path, starting from here, say, when it makes one complete rotation, the angle subtended at the center will be given by what? It will be definitely, it starts from here, comes back to here, so it will be 360 degree. Or in other words, it's pi, twice 2 pi, right? This complete angle is 2 pi. So, if it makes n rotations, then the displacement in time t will be given by, angular displacement will be given by 2 pi multiplied by n. Okay, so if it is so, then we have theta here. So you use this equation, theta equal to omega naught t plus half alpha t squared. Theta is given by 2 pi n equal to omega naught is 0, so this first term will be 0 plus half alpha t squared. Therefore, alpha will be equal to 2 to the 4, right? So 4 pi n. T square will come to denominator t square. So this will be our angular acceleration. Okay.